All right, let's talk about something that's all around us but completely invisible. We're talking about the world of gases, this constant chaotic dance of molecules. In this explainer, we're going to dive deep and make some sense of all that motion. Have you ever really thought about it? How can you smell a hot pizza from all the way across the room? Or why does a helium balloon seem to go flat so much quicker than a regular air-filled one? Well, the answer to both those things is all about how gas molecules move around. And believe it or not, these super common things are perfect examples of two really important concepts in chemistry, diffusion and effusion. We're going to break it all down so you'll get the what and the why.
Okay, here's our game plan. We'll start with what's behind a simple smell, then get into the nitty-gritty of diffusion versus affusion. After that, we'll look at Graham's law, see how to use it with some actual numbers, and finish up with a really wild, real-world application from the atomic age.
So, first up, a whiff of science. I want you to just imagine the air in the room you're in right now. It feels still, right? But it's actually a total storm of gas molecules zipping around at hundreds of meters per second. It's insane. But here's the catch. They aren't going in straight lines for very long. They're constantly crashing into each other. We're talking billions of collisions every single second. So their path is more like a chaotic random walk. And this wild dance, it's a key part of the kinetic theory of gases, and it's basically the engine behind everything else we're about to get into. All right, section 2. Diffusion versus effusion. These two concepts sound pretty similar, and they are related, but there's one key difference that you absolutely need to get. Let's start with diffusion. So, what is it? Put simply, it's just how molecules spread out to fill whatever space they're in. They're moving from an area where there's a lot of them, a high concentration, to an area where there are fewer of them. Think back to that pizza. All those delicious aroma molecules are packed inside the box. Once you open it, they don't just stay there, right? They spread out, they mix with the air, and eventually the whole room smells like pizza. That's diffusion. Each molecule is just bouncing around randomly, but the overall effect is this movement from high to low concentration until it's all mixed up. Now, effusion is a little different. It's a more specific situation. It's not just about general mixing, it's about escaping. So picture the gas inside a balloon. It's all packed in there, under pressure. If there's a tiny, tiny pinhole, those gas molecules will find it and zip through it one by one to the outside where the pressure is lower. That process, that escape through a tiny opening, that's effusion. So let's put them side by side to really nail it down. Diffusion is all about molecules spreading out and mixing together in an open space. Think perfume in a room. Effusion, on the other hand, is about molecules escaping through a tiny pinhole in some kind of barrier. Think air leaking from a tire. So if you remember just one thing, remember this. Diffusion is mixing, effusion is escaping. Got it? Okay, section 3, let's meet Graham's law of motion. So we know these gas molecules are flying around, but can we actually predict how fast? Well, back in the 1830s, a Scottish chemist named Thomas Graham got really curious about this. He spent a ton of time carefully measuring how fast different gases escaped through tiny holes, and what he found was this really elegant, simple mathematical rule that we now call, you guessed it, Graham's law. And here's the law itself, straight from the man himself. Now, inversely proportional to the square root of the mass sounds a bit fancy, but the core idea is super simple. All it really means is that heavy gases are slow and light gases are fast. That's it. As the mass of a molecule goes up, its speed goes down. It's a really beautiful and simple relationship. And this is what it looks like as a formula. Now, why does this work? Well, at the same temperature, all gases have the same average kinetic energy. And if you remember, kinetic energy is 1/2 mass times velocity squared. So for the energy to be the same, if a molecule is really light, its velocity has to be really high to make up for it. And you can see that inverse relationship right in the equation. See how the rate of gas A is on top on the left, but its molar mass, that m sub A, is on the bottom on the right? That's the inverse part in action. All right, section 4, putting the law to work. Enough with the theory, let's actually plug in some numbers and see what this thing can do. This is where it gets really cool. So here's our first problem. We're going to compare the effusion rates of hydrogen gas and oxygen gas. Now, hydrogen is the lightest element there is, and oxygen is way heavier. So common sense tells us hydrogen's going to be faster, right? But the real question is, exactly how much faster? Okay, so the process is pretty simple. First, we just set up the ratio from the formula, rate of hydrogen divided by the rate of oxygen. Next, and this is the important part, we plug in the molar masses, but we have to flip them. So oxygen's molar mass, which is about 32 grams per mole, goes on top, and hydrogen's, which is 2, goes on the bottom. So now we've got the square root of 32 over 2, which is just the square root of 16.
And boom, there's our answer, 4, or a 4-to-1 ratio. That means hydrogen gas literally effuses 4 times faster than oxygen. See, we didn't just guess it's faster. Graham's law gives us a hard number. That's pretty powerful.
Okay, let's try a different kind of problem. This time, we're not dealing with rates, but with time. We're told it takes 243 seconds for some xenon gas to effuse. Xenon is a really heavy gas. So the question is, how long would it take for the same amount of neon, which is much lighter, to do the same thing? We should expect it to be faster, right? Which means less time.
Now here's the only tricky part you have to remember. Rate and time are opposites, right? A faster rate means a shorter time. So when we set up our ratio using time instead of rate, we don't flip the molar masses. The time for neon over the time for xenon equals the square root of the mass of neon over the mass of xenon. See? No flipping this time. After that, it's just plugging in the numbers and solving for the unknown time. And when you run the numbers, you get 95.3 seconds. And that makes perfect sense, right? It totally fits what we predicted. Neon is way lighter than xenon, so of course it gets out of there much, much faster, in less than half the time, actually. Okay, last problem, and this one shows just how useful Graham's law can be in the real world. Check this out. We can actually use it to identify a mystery gas. If we know that an unknown gas effuses, say, 1.66 times faster than a gas we do know, like carbon dioxide, we can actually work backwards and figure out its molar mass. And molar mass is basically a chemical fingerprint. So here's how we do it. We start with the usual formula. The rate ratio, that's our 1.66, is equal to the square root of the molar mass of CO2 on top, that's 44, divided by the molar mass of our unknown on the bottom. To solve for the unknown, we just need to do a little algebra. First, square both sides to get rid of the square root, and then just rearrange the equation to get the unknown molar mass by itself. And what do we get? A molar mass of 16.0 grams per mole. Now, what has a molar mass of 16? Well, if you know your basic chemistry, you know that's methane, CH4. That is so cool. We literally just figured out the identity of a substance just by timing how fast it escaped through a hole. Amazing. Okay, final section, an atomic application. We've been doing these neat little lab problems, but it turns out the simple idea about gases escaping through tiny holes was at the absolute heart of one of the biggest, most world-changing scientific projects in all of human history. So, to build nuclear reactors or weapons, you need a specific kind of uranium, uranium-235. The problem is, in natural uranium ore, almost all of it is a slightly heavier version, uranium-238. And since they're the same element, you can't separate them with normal chemistry. They are chemically identical. The only difference is that tiny, tiny difference in mass. So, what did the scientists on the Manhattan Project do? They came up with an ingenious plan. Turn the uranium into a gas, uranium hexafluoride, and use Graham's law to separate the lighter U-235 from the heavier U-238. They applied this simple law on a massive industrial scale. And just look at this table to see how incredibly difficult this was. The mass difference is tiny, which means the speed difference is even tinier. The lighter U-235 gas only effuses 1.0043 times faster. That's a difference of less than 0.5%. It's almost nothing. So to get the uranium pure enough, they had to build these enormous facilities to pass the gas through thousands and thousands of barriers, one after another. Each step made the gas just a tiny bit more pure. It was literally Graham's law, just done over and over and over again. I mean, think about that for a second. This is the perfect story about why basic science is so important. A simple little law figured out by a chemist in the 1830s just by watching gases became the absolute key to the entire atomic age more than 100 years later. It really makes you wonder, right? What other simple, fundamental ideas that we're discovering right now are just sitting there, waiting for someone to find the right problem to solve that could, change the world all over again?